it? Yeah, so last lecture, we discussed Losser theorem. For every symmetry, for every continuous symmetry, there's a conserved current, okay? And then we also started talking about relativistic quantum mechanics, how we want to unify special relativity and the quantum mechanics, okay? So the most immediate idea for that is what's called relativistic quantum mechanics. And the most immediate generalization of the Schrodinger equation. So if you have, so at the end of last lecture, we talk about, say, the most immediate generalization of the Schrodinger equation, which so if you have E equal to, say, P squared divided by 2m, and then you go to non-relativistic quantum mechanics Schrodinger equation, okay? And now if you have E squared equal to P squared plus m squared for relativistic particle, and then you get what's called the Klein-Gordon equation. And again, this psi has the imputation of the wave function. So this describe, and then this. So if you as a generalization of this, then this meant to describe the quantum mechanics of a relativistic free particle, say of mass m. Okay, of mass m. So here the psi tx is the wave function of a relativistic particle. Relativistic particle of mass m. Okay? And we also notice that this equation actually is the same as the simplest field theory equation. So we also talked about a simplest scalar field theory, classical. So here is a simplest classic simplest scalar field theory. So this theory you can write down an axiom of the form so this is the simplest theory you can write down, and then a relativistic invariant theory, and then the equation of motion of this. So this is you view this as a classical field, and again this has the equation of motion have exactly the same form as this equation. So but now here phi again is a function of tx. Now has a completely different physical interpretation. So here is this is a classical field. Okay, so this is a classical field. Okay, so in this case, the interpretation of the x in here and in here is very different. Okay, so not only phi and psi, the physical interpretation are different. The physical interpretation of x also here are different. Here x is just a label. It's a label for the location in the space which we define this field. But here the x is the eigenvalue of the position operator for this relativistic particle. Okay, and so they have very different physical interpretation. And so let me just label this equation by 1, label this by 2, and this by 2 prime. Okay. So we also mentioned that this 1 has the interpretation of this as the wave function for relativistic, as the equation for relativistic quantum mechanics has a number of difficulties. So the first is that, as you will show in your PSAT 2, there's no sensible way to define a positive definite probability density. Okay. So if you want to interpret this as a wave equation, then you must have a way. Then you must have a probability density, because in quantum mechanics, probability should be conserved. Okay. And the second difficulty is that there's a negative energy state because of the square. Because when you take the square root, then you get the minus sign, and then there's negative energy state, which you cannot avoid in quantum mechanics, even though classically you can just throw them away by hand. Okay. And the third thing we mentioned at the end is that for relativistic wave equation, you can describe fixed number of particles so the particle number cannot change. Okay, so this equation describes a single particle, and if you want to describe two particles, then you need to write down a separate equation for a different wave function. So this is for the two particle wave function will be like this. Okay, and etc. Okay, but this does not really make sense in a relativistic system, because we know that in the relativistic system, E equal to mc squared, any case you have enough energy, then you should be able to create particles. And then that means the number of particles in the given process is not conserved. Okay, so if you want to use your quantum mechanics to describe a process, and then that's, you cannot have a formalism which the number of particles is fixed, which you cannot change. And so this is actually the most fundamental difficulty, okay, is that you cannot change the number of particles. And related to this difficulty is this interpretation. Here we say, now if you want to we say in here, there's a fundamental asymmetry between the t and x. Okay, also, yeah, maybe let me put it as 4. There's also fundamental. An additional difficulty, there's a fundamental asymmetry between t and x. So here, in the wave equation, t is just a parameter which we describe the evolution, but x is the eigenvalue of quantum operators, eigenvalues of quantum operators, say corresponding to, say, hat. By putting a hat, we denote the corresponding quantum operator. Yeah, so this is the eigenvalue of position operators. And this asymmetry becomes even more pronounced, say, if you consider two particles. Okay, you have two x here, but there's only one t. Okay. But so those, because of those fundamental difficulties, okay, so if you connect this 1 to 4, so we conclude that the relativistic quantum mechanics defined in the sense that you write down a wave equation, and for a wave function don't even cannot be a fundamental description. Okay. But yeah, but relativistic quantum mechanics just refers to this kind of wave equation. Okay. So at most, this can be approximate approximation. At most, this is approximate description in situations, say there's no there's no particle creation or annihilation. So in case which your particle number is fixed, and then you can use this as approximation, okay? But it cannot be a fundamental description. For example, later we will talk about the Fermionic version of this wave equation. So this will describe a particle without spin. So later we will describe the analogous equation for electrons for spin half, and then that can indeed be used to describe electron in the hydrogen atom, as far as you don't create new electrons, etc. Anyway, so relativistic quantum mechanics can only be described as some kind, considered as approximate description. Okay. But now, if you want to unify special relativity and quantum mechanics together, it turns out that the right formulation is just quantum field theory. Okay. So it turns out that the quantum field theory, addresses these difficulties. Okay. Okay. So it turns out that the right way, so if we want to describe quantum mechanics, say, of relativistic particles of mass m, okay, as we want to do here, it turns out the proper thing to do, which is a little bit unintuitive at first sight, is to start with this field theory, okay, which seemingly have nothing to do with relativistic particle, but to start with this classical field theory, and then quantize it. Okay, it turns out once you treat this theory as a quantum field theory, and this becomes a theory of arbitrary number of relativistic particles of mass m. Okay, and so that's the non-intuitive part, and that's the one of the miracle, say, of the field theory, is that automatically give you a formalism for treating arbitrary number of particles. Okay, and yeah. And also in field theory, so both t and x are parameters. Okay, even though x only labels your location, so both t and x are parameters, and so you can easily to make them to be on equal ground to be compatible with special relativity. Okay. Good. So any questions on this? Okay. So we will see that the right framework is quantum field theory. Okay. So finally, as the last motivation for quantum field theory, we quickly describe the last. So the field theory can also arise as a limit of discrete systems. Okay, and this is the most relevant for condensed matter physics, for example. So let's just consider, say, let's consider 803 example. Okay, so let's imagine you have just number of particles, a number of the atoms, say, on the chain. Okay. And then they're connected by some springs between them. Okay, so this is consider this to be infinite. Okay, and the spacing between them, say, is a. So atoms are fixed on some lattice point, and the lattice spacing is a. Okay. So we can label the each particle by their position. For example, this is x0, this is x1, this is x2, etc. Okay, and the typical particle is xn. The location of nth particle is xn, and so we can also introduce the deviation between the equilibrium position of each particle. So let's call it eta n. Okay. So now let's consider the dynamics of eta n for this theory. And so this is just deviation of the nth particle from its equilibrium position. Okay, so xn0 is its equilibrium position. So now if you write down the Lagrangian for this system, so we can easily do, you just write T minus V. So T is the kinetic energy, and V is the potential energy. So we can just write it as sum over n over all particles. And then let's assume they have the same mass. Let's write mu eta n dot square. Okay, so this is the kinetic term. So mu is the mass for each particle. And then their potential, let's assume at each point there is also, then there's some interaction. So because each particle are connected by the spring, and so there's a harmonic force between neighboring particles, okay? And now let's imagine also there's a harmonic potential which traps this particle itself at each location. Okay, so this is a very simple spring and the particle problem which you encounter, say, in 803. Okay, is this problem clear? Okay, I assume most of you have seen this problem before, and your task in 803 is actually to find the normal modes, say, of this system. Okay. And in 803, you also described that we can, in the equal to 0 limit, say if the lattice spacing is very small, and if you are only interested in the behavior of this system at a very large distance, say the distance much larger than A, then you can essentially treat this system as a continuum. Okay, you don't have to resolve individual particles. And so we can just in the equal to 0 limit, so can treat the chain as a continuum of particles. Okay, and so each eta nt you replace it by eta xt. So x label is position. Okay, so x label is position, and t describes the dynamics. Okay, so eta is the deviation at the location x, and it's dependent on t. Okay, so this is the oscillator. And then sum over n in the Lagrangian. Then we can replace it by integral over dx. Okay, and now you just treat this as a one-dimensional continuum. So it's some integration of dx. But of course here there's a label lattice spacing. So the infinitesimal here the element is a. So a times the sum over n. You can replace it by dx. Okay. A is the lattice spacing. And now you can just write this Lagrangian in terms of continuum theory. Okay, now you can write this Lagrangian in the continuum theory, and then let's just do it. So, so we can write it, let me just write one more step. So you can write it as sum over A. We take the A factor out, because the A factor out have to be changed into integration. And then you have 1/2 mu divided by A, eta n squared, minus 1/2 lambda A. So I just slightly rewrite this Lagrangian so that it's easy to take the continuum limit. So we have taken the factor of A out, but for this term, because this can sense the difference between the two, and we also divide it by A in the downstairs, and then we need to multiply A upstairs, and then there's A in the front. Okay? And now the continuum limit, you can just replace this by integral. And now you can just write it as 1/2 mu tilde eta dot square. So now eta n just replace it by eta xt. And here, let me call it lambda tilde partial x eta square. And this term, we can just replace it by the derivative of eta. And then this is just become 1/2 sigma tilde eta square. Okay? And the mu tilde, of course, is mu divided by A. Lambda tilde is lambda times A, and sigma tilde is the sigma divided by A. Okay, so the continuum limit is that those quantity has to be fixed. Okay, the tilde, the quantity has to be fixed. And then we have a continuum Lagrangian. Okay, and then we have a classical field theory. And this theory is essentially the same as that theory. Okay, so if you take this factor mu tilde out, okay, if we take this factor mu tilde out, okay, so let me just take this factor mu tilde out in the front, just up to overall factor. And here is lambda tilde by, divided by mu tilde, let's call it V square. And this becomes sigma tilde divided by mu tilde, let's call it M square. So the V square is equal to mu tilde is equal to the lambda tilde divided by mu tilde, and the M square is equal to sigma tilde divided by mu tilde. Okay? And then this is just essentially identical to that theory when V equal to 1. Okay, so when V equal to 1, become the same as just 2. Okay, equation 2. So V equal to 1, of course, corresponding to relativistic case, speed of light. But in general, this describe can describe but in general, this is a non-relativistic. Yeah, in general, this can be just a non-relativistic field theory. Okay, for other values of V. Okay. So this is. So even though this example is very simple, but this is actually a very general ways that we can treat many condensed matter systems, which often involve a lattice, say because it's solid, you can imagine all the atoms are on the lattice, etc. And if you're only interested in the very microscopic behavior, then you can treat solid as a continuum. Okay, and now you can now if you're interested in the quantum mechanics of such a system, then the quantum field theory then naturally arises. Okay. Good. Any questions on this example? Yes?
So the limit that V goes to 1 is the same as lambda and mu being comparable. So what does that, I guess, physically mean?
Sorry?
So the limit of
Yeah.
is like saying lambda is the same as mu?
Yeah.
So what does that physically mean? So you're saying the strength of...
Yeah, just corresponding to the case that it just tells you that the relativistic limit is special. Happens at very special points.
But I guess why is that the relativistic limit? Like, to me, lambda is like the strength of your spring, and then mu is your mass. So
right.
Them being comparable, how does that?
Yeah.
Is it the same thing as the relativistic?
Yeah, there's not much you can read from here. Yeah. It's just like when you choose some special parameters, then you can have a relativistic limit. Other questions? Yes.
Yeah. So you said that you could use this to treat some condensed matter problems.
Yeah.
Yeah. So these are all scalars, right?
You can also have you can also have tensors or vectors. Yeah.
Okay.
Yeah.
So like, what would you treat with this? Like phonons?
Oh, you can treat, for example, you can treat phonons. You can also treat spins. And say, for example, if you have an Ising model, just consider lattice of spins, and then the average spin, and then you can treat it as a scalar field, and then again you can write down a field theory. Yeah. And actually, the breakthrough of the phase transition in condensed matter physics to understand what phase transition is really about and describe the behavior near the phase transition, and precisely coincided with the development of field theory. And actually increased our understanding of quantum field theory. Yeah. Good. Other questions? Okay, good. Just to summarize what we have discussed so far, all paths leads to QFT, okay? So we have described three paths, but they're pretty general. First is that the quantum dynamic, we often are interested in quantum dynamics of some classical fields say such as, say, electric magnetic field or space-time metric if you are interested in gravity, etc. Okay, so in this case, we already have the classical field theory, but we know the world is quantum, and we want to understand what's the quantum version of it. And the second is that it unifies special relativity plus quantum mechanics. Okay, so you need the field theory to unify them. And the third way is that it's the a large distance description of discrete systems. Okay, so yeah, just combining all three elements together, they cover many, many areas of physics. Okay, they cover many, many areas of physics. Good. So now we can say a little bit about the plan for the whole semester. Okay, so here is the plan. So this is like just rephrase of the outline, which So the first thing we do in chapter 2, so here is chapter 1. In chapter 2, we discuss the simplest field theory. Just discuss this equation 2, okay? The theory of 2, okay? 2 and 2 prime. Yeah, the prime is its equation motion. So yeah, in physics, we always start with a simplest example. Okay, we always start with simplest example, and so that's is the one we will start with. So what we will see is that this describes that field theory describes spinless. There's no free massive particles. Okay. Okay, so we will see when we quantize that theory too, and then we get the theory of free massless or free spinless massive particles. Okay. So you say, oh, that's a little bit boring because in this theory it's free. The particle, by free means they don't intact. Okay, the particle they just don't intact. And then in chapter 3 we will add interactions. We will describe how to treat interactions, okay? So we will introduce interactions and tell you how to treat the interactions between those particles. Then in chapter 4, we go to the real physics. So this scalar field is also real. Say, for example, can be used to describe the Higgs boson, okay? But the Higgs boson maybe is a little bit far from what you normally think about. So in chapter 4, we will go to something which is much closer. We'll talk about the theory of electron. So this is called the Dirac theory. So this theory describes free but spin half particles, okay? So this is a theory of electron, okay? When we neglect these interactions. Okay, so this is the free spin half particles. And then we move on to the Maxwell theory. So this is the theory of the quantum electric and magnetic field. Okay. So we quantize the Maxwell theory, say without source, the vacuum Maxwell theory, and you find you get free, again, there's no interaction, massless spin 1 particle. You get a series of massless spin 1 particle. So this is what we call the photon. Okay, so this is the quantum for electromagnetic field. Okay, and then sorry, did I? So this should be chapter 5 now. I think I lost my count. So now go to chapter 6. We combine the 4 and the 5 together. Okay, combine electrons. So photon normally we denoted by gamma. Combine the theory of electron and a photon together, and then plus interactions between them, and then we get the so-called quantum electrodynamics. So this is called QED. So QED is very general, essentially covers all the quantum phenomena, macroscopic phenomena up to, say, weak interactions and strong interactions. If you don't go inside the nucleus, and or don't go to a very high energy, I think that covers essentially most of the physics. And then we will describe how to and then that will be the end of this course. So do you have any questions on this? Okay, so this is a roadmap. Yes.
Do these chapters correspond to also chapters in the textbook, or just chapters in the lecture notes?
The chapter in the lecture notes. Yeah. Right. Good. Other questions? Yes.
I'm just curious. Is gluons included in the free massless spin-on particle?
Sorry.
Is gluons included in those free massless spin-on particle?
Yeah, gluon is also massless spin 1, but gluon actually they interact with themselves. And so gluon is different. So gluon, to describe gluons, you have to wait for quantum field theory 2. And so the thing about the photon is that the photon don't interact with itself, but the gluons interact with itself. Okay. Yeah, so essentially we treat everything except gluons. Yeah. Other questions? Other questions? Okay, good. So now we can just move to chapter 2. Now we are talking about this theory. Okay, so actually I should not erase it. So now we talk about this theory. So because this theory describes free particles, so we call it free scalar field theory. Okay, so this is the theory we are interested in. So now we will describe how to quantize this theory. Okay. Good. So first, we will quickly go through the quantization of harmonic oscillator, which you should already have done in your P set, and so we can do it relatively fast. So quantization of harmonic oscillator in the Heisenberg picture. So we will see that once we understand this example in the right way, and then quantizing this field theory become trivial. Okay, and quantizing this field theory become trivial. Okay, so let's start with quantum harmonic oscillator. For simplicity, I take the mass to be 1, and take the frequency to be 1. Okay. Yeah. Let me put the frequency here. 1/3. Okay, let's take the mass to be 1. Okay. And so for this series, so this is a simple harmonic oscillator because you have seen it maybe for the most of your intellectual life. And so P will be x dot. So momentum, the conjugate momentum is x dot. And so the Hamiltonian is the P squared divided by 2 plus 1/2 omega squared x squared. Okay? And the equation motion is x dot double dot equal to x squared. Okay? So let's first look at this theory, look at harmonic oscillator as a classical theory. So for classical theory, we know how to solve this equation. We just need to solve this equation. So classical solution. Just given by xt equal to a cosine omega t plus b sine omega t. And a and b just some integration constant. And for convenience, I can also write it in the complex form. Write it as following: equal to a exponential minus I omega t plus a star exponential I omega t. And a is some complex constant. And again, it's an integration constant. I just rewrite the integration constant slightly differently. Okay? So these are just integration constants. So now, yeah, so this is a complete solution of the problem. So now let's go to quantum. So when we go to quantum, and then we replace, then this classical dynamical variable then become the Heisenberg operator, become the quantum operator. In particular, in the Heisenberg picture, and then this operator will depend on time. Okay, and now this equation become operator equation. Okay, so now maybe I should label my equation. So now this star become the operator equation. Now star is the operator equation for x hat. So you have exactly the same equation as a classical equation, but now the interpretation is different. And now the x hat become now the x become the operator equation. So now the solution. Now let me call this star. So this still solves that equation. Okay? So this still solves that equation, except, so these are just C numbers, because this is a function of t, these are C numbers. But now x becomes so now quantum mechanically, so this now become the quantum solution. Okay? So now it hat. So this still solves that equation. So quantum mechanically, this becomes a hat. Okay? And so this still solves that equation, but these are C numbers. The left-hand side is the operator, and it can only be that A hat and B hat are operators, and also A must be operators, and the star will replace it by dagger. Okay, so now, say, now A, you just go to A hat, and A star goes to A dagger, A hat dagger. Okay, now these are integration constants for the operator equations. So they are just now they become constant operators. Okay, so they're just constant quantum operators. Okay, they're just constant operators. So they are integration constants for your quantum operator equations. So now the solution. So now this is your quantum solution. Okay. So this is the form we will often use. Okay. You can also use that form, but the equivalent. But this is the form we will often use. Okay. You can also, from here, you take the derivative, you can find the p. So again, this has become an operator equation. You take the derivative on x hat, and maybe you find p, etc. Okay. Yeah. So the p hat t. You just take a derivative. Okay, and then you can just work it out. It's very easy. So now, so this equation just, so we already solved the quantum problem. Okay, so because we find the full solution to the quantum operator equation, except that we still need to impose the canonical quantization condition. So this is just equal to I. Okay, so the standard. So if you plug in the expression for x and the t and the p into here, and then you find that a and a dagger, the commutator is equal to 1. Okay, so this is your familiar creation and annihilation operator for harmonic oscillator. Okay, for harmonic oscillator, and now we can also use the A to build the Hilbert space. So because A are because all your operator now, because x and t, x and p are expressed in terms of A and A dagger. So essentially any operator of this series can all be expressed in terms of A and A dagger. Okay. And then we can just use A and A dagger because A and A dagger essentially they are fundamental building block of your full quantum theory. And then we can also use that to build the Hilbert space. So the Hilbert space is defined by the lowest state is annihilated by A, and then the higher state are obtained by acting a dagger on the ground state. Okay. So this is your full theory. Okay. So this is your full theory. And so now you can compute anything in this theory just with those knowledge. Okay, just with those knowledge. So any questions on this regarding the harmonic oscillator? Good. Okay. So let me just summarize. So this is maybe very familiar, but let's summarize the rule we have been using. Okay, summarize the steps. In quantize the harmonic oscillator, and then the same steps can be used to quantize the field theory. Steps of quantization. So we make it general. So first, so the zero step is that the classical equation motion with quantum operator equation. Okay. Then the first step is to find the most general solution to find the most general solution to classical equation motion. Yeah, just to equation motion. Okay. And then when you go to quantum, and then you just promote the integration constants in your classical solution in the step 1 to constant operators. constant quantum operators. Okay. So this gives the then you have the full time evolution at the quantum level. Okay. So now you know how the quantum operator evolves, and then you impose canonical quantization conditions. Okay, so that will tell you the commutators between those integration constant operators. Okay, just as we do here, and then constant operators in Q. Now you also know the commutation relation between them among them, and then now can be used to generate the Hilbert space. Okay. So this step and 1 to 4 are very general, and if you can do it, and then you can essentially do it apply it to any system. Say 1 degree harmonic oscillator is 1 degree freedom. You can apply it to 2 degrees freedom, 3 degrees freedom, and also to field series with infinite number of degrees freedom. Okay, and now we will apply this to field series. Yes.
You get finite dimensional Hilbert spaces from this procedure?
For this procedure, you cannot, but you can get finite dimension. Yeah, because the finite dimensional Hilbert space don't have the classical analog. So here we start with a classical system, and then we quantize it. And the quantum system with a finite dimensional Hilbert space, they're essentially intrinsically quantum, and and like spin. Spin is an intrinsic quantum thing. Yeah. Yes.
Like this also has to do with Stonewall Gordon, right? The fact that there are no finite dimensional representations of these dagger operators, A and A dagger.
Yeah. It's just because they don't have. The reason is just they don't have classical counterpart. Yeah. Yes.
Is it always true that the constant operator is sufficient to generate the entire Hilbert space?
Yeah, because if you think about it this way, that's a very good question. Because let's just look at this harmonic oscillator, and then you can try to generalize it. Because they are integration constant of the x and the p, then any operator in your theory can all be expressed in terms of A and A dagger, and then your Hilbert space must be you must be able to generate the Hilbert space using them. Yeah, because they are the building blocks of your whole operators. Yeah.
How do you get the vacuum state? Like, is there always a generalization of vacuum state?
Yeah. The vacuum state here is based on is come from the energy, right? So once we solve x and p, and then we can write the Hamiltonian in terms of x and p, and then you just look for the lowest energy state, and then you find the lowest energy state just satisfy this equation. Yeah, and then from there you can find other states. Yeah, the same thing we are going to. Yeah, the same strategy we are going to use for the for quantum field theory. Okay, good. Okay, good. So now become a mechanical. We can just apply this to this theory. Okay, we can just apply this to this theory. And now let me add here. So here the canonical momentum density conjugate to phi is I called pi before. It's just the time derivative of phi. And the Hamiltonian density, you can find it explicitly, is pi squared plus 1/2 Okay? And then this is the classical equation motion. Okay? So we can, now let's just solve this classical equation motion. So this equation can be, so this equation is easy to solve because of the translation symmetry. Okay, you can just do a Fourier transform. Okay, so we can Fourier transform. So now let's do the, we can Fourier transform. So 2 prime can be solved. Okay, so we can just write phi x equal to exponential minus iet plus I k dot x. Okay. Okay. So, and then you can see that this just solves the. So this is provide a basis of solutions to 2 prime. Okay. It's just a plane wave. Okay, just plane wave. So now when you plug this into there, then you just get the dispersion relation. E square should be m square plus k square. Okay, so we'll denote this as omega k square. So omega k is defined to be just the k square plus m square. Okay. So E, when you take the square root of E, so you can take plus minus omega k. Okay, can be plus minus omega k. So we normally call the solution, we normally separate so for historical reasons, okay, we normally define UK x to be exponential minus I omega k t x. So okay, now we have inserted the positive root of E. So this is normally called the positive energy solution. Even though this name is a little bit misleading, okay, so actually we don't define the energy actually. Later we will see this is not really the energy of a particle, and so this is just a traditional name. Okay, this is just a traditional name, conventional name, and then you can define the complex conjugate of k. And now you have then corresponding to you have minus omega k in there. So we take this complex conjugate. And so this is called the reactive energy solution. Okay? So altogether, they form a complete set of solutions. Okay, so complete set of solutions. So complete basis, a complete set of, complete basis is formed by UK and the UK dagger, UK star for all k. Okay, for all k. Okay, so these are the these are the complete set of solutions to that wave equation. Okay, so that's just any questions on this? So this is just like classically, this is just like a wave. Okay, just like a plane wave. Okay, which you should also have seen in 803. Yeah. Good. So now we can find so now we can write down the most general. So this is a basis. So these are the counterpart of the exponential plus minus omega t here. Okay, so now we can write down the most general solutions by just putting in the integration constant. So the most general classical solutions. So you can just write phi x equal to integrate of all possible value of k, because this is for all k, so we just sum of all of them. And so this factor is for just for convenience, okay? It's just a convention. You don't have to put it here. It's just a convention. And then we have ak uk plus ak star uk star. Okay? So this is just the most general set of solutions with ak and ak star as integration constant. So this is a full set of the integration constants. Okay. Good. So now, when you go to quantum level, so now we can just follow the rule. Okay, we find the most general classical solution, and in the quantum level, we just promote this to be operator. You just put a hat there and change this to dagger. Okay, so now this becomes your basis of quantum operators. Okay, so these are the full set of constant quantum operators. And this solves your theory. Okay, so this solves the operator equation. Okay, this solves the operator equation. So now the next thing is to impose the canonical commutation relation. So first we have to, now we have to do a little bit thinking, okay? So far it's just straightforward, but now we have to do a little bit thinking. So for finite, for harmonic oscillator or for quantum system of a single variable, you just have x, you just have this. You just have these. And now we need to come up with a generalization of these to a field theory. Okay? So we need to come up with a generalization of that to field theory corresponding to phi x. So now let me make the time and the spatial coordinates separate. And its conjugate momentum is pi, okay? Conjugate momentum density. So we should do them at the same time. Remember, T is the same evolution operator, so they have to be evaluated at the same time. Also, it's an equal time. Canonical quantization condition is always at the equal time. But X is a label of operators, so X, they don't have to be the same, okay? So here can be X, here can be X prime, okay? So now we have to come up with a generalization of what is this quantity for field theory, okay? So now we just need to do a little bit guesswork, okay? You can easily guess it. So before we do that, do you have any questions on this? Yes?
So X has already stopped being an operator in this picture?
Yeah, X is always So x is always here. Is always just the label of the spatial location, right? Yeah, it's a label for the It's your field theory label. Yes.
So in this procedure, I guess you always end up with your operators as being constant in time. Is there any way that you can get them where it's like the evolution is more complex rather than just a constant operator and the phase factor?
Yeah. So normally, if you have second order differential equation, you always have some integration constant. Yeah, that's it. Yeah.
So that carries forward all throughout?
Yeah. Other questions? Yes?
Should it be obvious why the classical equation of motion translates directly into the operator equation of motion?
Right. Yeah. So that's a very good question. So that's just an extension of our usual procedure for the quantum mechanics. So the usual procedure when you even just for harmonic oscillator for single variable system, you have this correspondence between the classical system and the quantum system. When you quantize the classical system, then the classical equation motion become a quantum operator equation. Here we just use the same rule because quantum field theory is just the theory of infinite number of discrete freedoms. We are not changing the rule of quantum mechanics, and so that's why we just again just promote the classical equation into the operator equation. Other questions? Yes?
One way of understanding like the Heisenberg equations for the quantum mechanics is that relate to like the Poisson brackets for like classical theory. Is there something like that for field theory as well? So I guess the
Yeah, there is, yeah. So classically you can define the Poisson bracket between the classical field variables, and then quantum mechanically just become quantum commutators. Yeah, you can also do that. That's right. Yeah, so one way to come to this is you first describe, first you need to generalize your standard Poisson bracket for finite number degrees freedom to classical field theory, and then you can just generalize that to the to quantum. Yeah, indeed. That's one route of doing it. Yeah. Okay, other questions? Good. So we will just guess the answer. Okay, the answer is very easy to guess. So remember, if you have a single x and p, that's what you have. Okay. But if you have more than one particles, if you have more than one particles, say just hint, say you have multiple particles, system in quantum mechanics, and then you have xa and pa as your dynamical variable. So a equal to 1 to say n, say the number of particles, okay? And then your canonical quantization condition just become xa t pb t equal to I delta ab, and different xa commute, and different p commute. Okay, different p commutes. Okay. For some reason, let me just put this out. So now this A and B are essentially just replaced by x and x prime. So x and x prime are just continuum version of those A and B. Okay, remember, we kept emphasize the x and the x prime are the labels of your degrees of freedom. So now you can just guess. Okay, so we must have the following scene. So from here, we must have phi tx phi tx prime must be 0, and pi tx, so pi is the analog of p here. Yeah, so those are operators. Tx prime must be 0, and then phi tx with pi tx prime should be something can only be 0 when x not equal to x prime, can only be non-zero when x equal to x prime. Okay. Okay, as a generalization of these. Okay. And so you can guess. So what should this be? So what? Yeah.
Dirac delta.
Yeah, this should be just Dirac delta. Okay. But now you can ask the question: why has to be Dirac delta? Maybe why should not be, say, the derivatives of Dirac delta? Okay. Say why should not be, say, 100th derivative of Dirac delta? And that question can be addressed just by from dimensional analysis. So here we know somehow this must be related to Dirac delta, and now let's decide. So now you can do the do a little bit dimensional analysis. So if we just write down the action, yeah, the action I have just erased. Sorry. So if you look back on the action, let me just outline the idea because I'm sure you can do dimensional analysis yourself. So if you look at the action, so the action is dimensionless in the lateral unit we are using. So if you, so from that you can deduce the dimension of phi should be 1 over L, so 1 over the length. Okay. And from the fact that the pi, where is pi? Maybe I have also erased. Is equal to phi dot, means pi should be dimension 1 over L squared. Okay, because you take the derivative one time, and then there's another factor of L. Then that means on the right-hand side here must be something 1 over L to a cube. Okay, because there's no other parameters here. Okay, yeah, because here there should be an I. Okay. And if it's a dimension 1 over cube, then can only be the delta function, not a 100th derivative of delta function. So this thing should be just a delta function. Okay. So this the convention that there should be an I, and then should be just the 3 delta function. And this indeed have the dimension 1 over L cube. Okay. Good. So now you can just plug. So you have the expression for x, for phi. You take the time derivative of this. You get the expression for pi. And now you can just plug them into here. You can just plug them into here. Okay. And then you can find the commutation relation between those AKs. Okay. And so this is a slightly tedious calculation, which is, however, a little bit fun, which of course I will leave you to do. So if you just plug them in, and then you can deduce the following commutation relation between A's. So this is I think this is in P set 2, but I can still change my mind. Yeah, I wanted to put in P set 2. So you find the commutator between A and the commutator between A dagger. Yeah, so now I will suppress the hat, okay? Because to write hat, I think over and over I will be too tired. So these are 0. Okay, so the commutation relation between A are 0, and A between A and A dagger. So this gives you 2 pi cube delta function in K. Okay, so this is a 3 delta function in K. Okay. So again, this is a straightforward generalization. say if you have multiple harmonic oscillators. So if you have considered the multiple harmonic oscillators before, and then the A between the different harmonic oscillators, because K prime are just here just corresponding to, essentially you have, here it just is, essentially you have infinite number of harmonic oscillators, and each one of them labeled by a K. Okay, so this is just like, essentially we find, let me just write it here. So from those commutation relations, we conclude this theory, when we quantize, after we quantize it, become an infinite number independent harmonic oscillators, decoupled harmonic oscillators, labeled by continuous parameter K. So K is, K is the wave number. Okay? So for each K, there is A, and A, and so between A themselves is 0, between A dagger is 0, but A dagger, they not equal to 0. And so this is, again, the continuum generation of 1. Okay, this is a continuum generation of 1 because you have a continuous variables. Yes?
So how about the commutation relations at different times?
Then you cannot say for sure.
But like by Lorentz invariation, x and t be on the same footing, shouldn't we have the same?
No, but you see the quantization condition is in quantum mechanics. Quantum mechanics, t and x are not on the same footing. You can require your action to be x and t to be on the same footing once you start to quantize your theory, and then t will have a pronounced role.
Okay, so if I wanted to, so I couldn't write the commutation relation as functions of the 4-vector x.
No.
Is delta x.
No. The canonical commutation relation have to be imposed at equal time. Other questions? Good. So so essentially we just get, and now it's just trivial, okay? So you can just build up your Hilbert space. Essentially you just have infinite number of harmonic oscillators. Okay, just have infinite number of harmonic oscillators. And there's no surprise you get infinite number of harmonic oscillators, because we mentioned that this field theory can be actually written as a continuum limit of these particles on the chain, which in these 803 examples, you know that's just a harmonic oscillator. Once you find the normal mode, they're all just a bunch of harmonic oscillators. And this is just a 3-dimensional version of that. Okay. And now we will, today we are running out of time. So next time we will see that each excitations of the harmonic oscillator can be interpreted as a space-time particle. Okay, so that's the cool thing of it. And now you have this infinite number of harmonic oscillator, and now you can act. Now you can define the vacuum, and then act these creation operators on the vacuum. And now you find each excitation actually corresponding to a particle, and has the corresponding to a relativistic particle. And that's how you can have actually arbitrary number of particles in this theory. And because you can excite as many times as you want. Okay, each excitation is a particle. Good. Okay, so I think it's a good time. Yeah, we are 2 minutes, I think, early, but I think it's a very good place to break.